What is the spark to that thought? Your machine, you can give that spark to. We don't know where the spark comes from.
That's crazy to hear you say.
My name is Dr. Daniel Scodary. I'm a neurosurgeon here in St. Louis.
I'm Anthony Scodary, co-founder of Gridspace. I'm in a lot of these videos. I work in the field of artificial intelligence and deep learning at Gridspace, where we build systems that speak and listen to speech.
Well, this is a direct example of transmission of neural networks from father to son.
Yeah, exactly. So I thought we'd compare what we do with artificial neural networks
Sure.
with real ones.
You know, the neural networks of the brain have been studied all the way back into the 1800s. They've been doing gold and silver stains and all kinds of stuff, trying to figure out what connects to what. Over the last, I'd say, 25 years, those pathways have exponentially been understood. Although there's so much more to learn, we still don't understand it. As a surgeon, we're trying to figure out corridors to go around those neural networks without causing injury to the brain. You guys have, I think, the license to manipulate that without causing deficit.
Let's talk about like one neuron. So like in an artificial neuron, which is much simpler than a biological neuron, you have a bunch of input signals and then a weighted sum of them drives some sort of output function called an activation function. How does that compare to the axons and dendrites?
Everything begins at the nucleus, the body of the cell. There are basically two processes that come off that body. One is the axon that you mentioned, and it is the efferent. It goes out to transmit information. And then there are dendrites, which are the afferents that bring the information in. Now, those axons, when they go out, can either inhibit another neuron or activate another neuron. So there's positive reinforcement pathways and negative reinforcement pathways, which I bet you guys are kind of copying and making some of these neural networks.
Yeah, well, there can be positive or negative weights on it, which kind of is similar. Now, can you talk about like, so they use something called an activation function, where there's a nonlinear response of the inputs to the outputs that is meant to very loosely mimic the action potential. What is the action potential?
The action potential is a signal that's generated from the nucleus out the axon. And the nerve fibers themselves are made up of axons. And those signals are transmitted between nodes. There's sheaths of myelin around the nerve. And those action potentials, as they hit each node, can speed up and speed up and speed up, thus allowing an instantaneous response from whatever that axon is carrying, what kind of information. But they usually terminate on a dendrite and send information to that next cell. There are some pathways in the body that are only 2 neurons. For instance, a reflex, you tap on the knee, that's a 2-neuron system, that's it. And there's some in the brain, such things as thought and cognition that incorporate millions.
My cognition is a 2-neuron system.
Well, you guys from Stanford and MIT barely have 2 neurons working anyway.
Let's talk about learning. Machine learning trains artificial neural networks through a process called gradient descent, most commonly, not always. I guess the theory of learning for neurons, I've heard of Hebbian learning.
Well, you know, there's 2 kinds of learning in the human body that you don't deal with. We have to learn physical learning and we have to learn mental learning. What's the difference? I give you a set of questions to memorize the answers to. So you have to learn those by putting them into a memory bank by reverberation, by looking at it over and over. However, what if you swing a baseball bat? That's physical learning. You swing it, you miss. You swing it again, you get closer, until you eventually learn the pathway of learning to hit that ball. One is done in the temporal lobes, the cognition of learning. Learning of repetition physically is done in the cerebellum, where your ability to have sensitive movements is generated. Speaking
of sensitivity, I've heard that way fewer nerves per motor unit, or how's that work?
It depends which part of the body you're talking about. Fine detail like the finger, many, because it's such a fine movement. While something grossly like just the adductors of the hip don't need so many neurons. It's very selective in the body as what that part of the body has to do. Along with that, there is the ability to override those systems. Okay, you're trying to hit that baseball, and all of a sudden they throw the ball in a different place. Instead of swinging in the same area, you can override and retry to learn quickly based on vision. So there's a lot of override systems in the body to make corrections.
Got it.
Well, I'm not sure in artificial intelligence you have that ability to think at that level yet.
Yeah, well, in general, machine learning is very simple. It's basically you compute how big your air signal is, kind of like swinging the baseball bat, and then you just find how that air signal propagates backwards through all the neural network. My understanding is that they have never definitively found a back propagation mechanism in human neurons. So there might not actually be one. It might be, very different than the kind of, fire together, wire together kind of learning mechanism.
And I guess in artificial intelligence, you don't have the position of fatigue. While in the human brain, it fatigues on both standpoints. Whatever you're trying to do, it can get tired, low on glucose, oxygen. There's a lot of feeding mechanisms that I would think a machine doesn't suffer from.
By the way, so I think people always think of neurons as being like an electrical network, but
They are.
What part's electrical and what part uses neurotransmitters?
The axon that we talked about is basically a conduit, a wire. Each axon has what's called a neurotransmitter that it releases. And there are many different kinds, acetylcholine, epinephrine, norepinephrine. Based on what transmitter crosses that synapse to the next, will decide if it's an inhibitory or an excitatory pathway. In the last 10 years, there's been a plethora of new neurotransmitters that have been discovered.
Got it. Can you eat the brain?
You can eat the brain. As a matter of fact, there used to be a sign here in St. Louis downtown that sold cow brain sandwiches for 25 cents.
See?
And I have a picture of that I always use in my lectures. It's very high in cholesterol. And in certain organizations, it spreads disease. There's a disease in sheep called scrapie. That's a subviral particle called a prion. But when you get up to the upper highlands of New Guinea, and they still practice cannibalism, that prion disease elicits itself as something called kuru. And it's a neurodegenerative disease. In the real world, the settled world, we have a disease called Jakob-Creutzfeldt, which is prion disease that has an incubation period of about 20 years, and that can be spread by eating the brain.
That's mad cow disease.
It's related to mad cow disease. So yeah, you can eat the brain, and it's very high in cholesterol.
Is it have a lot of umami because of all the glutamate?
I don't know what that. You're from California. You guys probably eat it a lot out there, but here in the Midwest, we stick with hamburgers.
So let's talk about vision.
It's very complex. Vision in the human body is made to work out of two eyes, and that's what gives you depth, stereoscopic vision. But we have to coordinate visual fields.
Yeah.
Right and left visual fields. When I look and I'm seeing to the right, those two right visual fields cross to the left pattern across the optic chiasm and is transmitted to the left side of the brain and vice versa. So we can actually have deficit in half a visual field called hemianopsia or quadrantanopsia, just up in a quarter, or we can have complete blindness in one eye. All that is a very complex pathway that goes through modulators in the brain.
So let's start with the retina. I've heard the retina is actually the only part of the central nervous system outside of the cranial cavity.
That's why we look in people's eyes. There are 12 cranial nerves. The second cranial nerve, called the optic nerve, is a direct vision into the eye, the brain itself. If there's pressure inside the brain, we can see that on the optic fundi. We can see the squish of pressure and the spread of edema or swelling in the back of the eye. So indeed, you're right. It is our corridor of vision right into the brain itself of what's going on.
Perceptive fields in the optic nerve, the layers of edge detectors and then pattern detectors in the optic nerve and then part of the occipital lobe, inspired a lot of work on computer vision, which uses something called a convolutional neural network, where you also have edge detectors and then layered feature detectors that are very similar. I think one of the best understood parts of the brain in terms of how well it's been mapped in cats. What is a perceptive field and how does the optic nerve and occipital lobe work?
Well, it's very complex. So as I just told you, we're going to look at an object that is transmitted to the retina in an upside down pattern. And then those left or right visual fields are transferred back across to the optic nerve and then through some modulatory pathways and nuclei and then ultimately to the optic lobe, optic part of the brain, the occipital lobe. So it's a very complex changing of patterns, and it helps us make diagnosis and localization of lesions. For instance, the pituitary gland sits right under the optic nerves. And if we get a tumor there and it grows up and hits both optic nerves, you get bitemporal hemianopsia. It knocks out both visual fields on both sides. You're looking down a shotgun. So we can see we can make diagnosis of disease by looking at the complexity of deficit of visual fields.
Then after the occipital lobe, my understanding is that some of that information flows through the dorsal flow and some through the ventral flow.
Yeah, through the thalamus, which is a modulating. Now think about that. So if I hold up a sign and it says stick out your tongue, we'll start with that, something simple. It goes in, you read it, goes in through the visual fields, right, into the occipital lobe, and then it has to modulate to a part of the brain that you recognize through language to stick out your tongue. And there's going to be an expressive part of the speech and the receptive part of the speech center. So receptively, you recognize that command, and then that goes to the motor part of the brain, and you stick out your tongue. So vision is a very complex pathway that integrates with so many different things. Think about that. And how many people pass out from seeing blood, right? That's got to go through the limbic system. Now I get lightheaded just seeing blood, or you've seen somebody in a car accident. The adrenaline's flown. All that came in through the visual pathway, and then has to be modulated by other parts of the brain.
So is that different? I mean, how does that work in machine learning where it get, like, let's say, receives a text message and then has to vocalize a response to that?
Computer vision really strongly resembles, because it's so well understood neurologically, they know that convolutional neural networks, the way that the optic nerve and then a little the occipital lobe processes visual information initially is very similar. After that, I think it starts to break down. Like
I mean, I bet you could teach your computer to, if I hold up a red card and say, what color is this? It'll recognize red, blue, purple. But then if you give it a command what to do with that, now write a paragraph in that color, can it do that? Or what does that do to you emotionally to see red or blue? I don't think your neural network is at that sophistication yet.
So I'm gonna show you some pictures. I want you to tell me what emotion it evokes. Okay, here's the first picture here.
That's a dog. It's a Labrador. It makes me feel good, right?
All right.
So for me to feel that, I had to see it and integrate that into part of my brain that recognizes it as a dog that I had at one time. It brings back a memory, a yellow lab, and that I'm thinking, oh, what a cute little dog. I'm not thinking it's a raccoon or a girl.
All right, now I'm gonna show you this picture. Tell me what emotion it evokes.
That's my other son, isn't it? No, who is that?
It is.
Is that Nick? Well, I thought it kind of resembled that other dog. That's my son. It elicits a feeling of happiness, and I'm glad to see him. Pictures like that have to integrate into real deep parts of the brain.
And that's through that would be through the dorsal flow down to the limbic system?
It can be through either flow. There's ventral inputs and dorsal inputs into the thalamus. That little body, the thalamus, which is a nucleus in the center of the brain, is one of the most complex, highly organized modulators of the entire brain. And then out of the thalamus feeds into everything. Limbic system, motor system, sensory system. I suspect many of those complex pathways are in that very small little package. We rarely operate in the thalamus.
Would that be like comparable to like an architecture in an artificial neural network?
Yeah, there is an architecture there. And not only is it an architecture, each part of the brain has different layers of neurons.
Yeah.
The cortex will have 6 layers. Some of them will have 3 layers. So the architecture, as you speak of, is different in each part of the brain and how many inputs and outputs. So the architecture is very complex. I don't know in neural networks how complex the architecture is, or is it just a single wire?
Yeah, I mean, in general, neural networks, as we have built multimodal neural networks, so for instance, neural networks that have like vision and language or audition and language, what ends up happening is at some point you need to combine the information from the different modalities. Sometimes you see things where you have encoder-decoder networks where you encode down the vision, encode down the language input, put that into one abstract state, and then decode into maybe the next word you want to generate or something. But sometimes you actually just see the image gets tokenized along with words. When you have those encoder-decoder networks that are multimodal, it kind of resembles the thalamus in that it's a traffic cop between all these inputs and outputs, but to be honest, it's much less complicated.
And we, long ago, within the last 100 years probably, Dr. Brodmann was able to elucidate, if he took a brain on a picture areas, area 43, area 42, area 21, Brodmann areas, and we label those Brodmann areas with functional characteristics, speech, motor, sensory, things like that. So now the neuroanatomists said, okay, well, we know that we've got vision coming in. How does that interplay with Brodmann area 25 or 30, or which is motor or speech, or so all these complex pathways. Well, now as a neurosurgeon, with the MRI scanner, we're able to show these tracks on the MRI called tractography and look for corridors that we can operate within, leaving those tracks unadulterated so we don't cause injury when we're operating. Otherwise, they wake up with deficit. I mean, we're dealing with the very essence of that patient, their memory, their thought, their third grade, playing the piano, everything. That a millimeter or two can make a difference in how the rest of their life's going to be attainable.
So let's talk about language. A lot of the interest in machine learning in the last 2 years is because of big language models like ChatGPT, or what we do at Gridspace with speech and language.
Can your neural network speak?
Our neural network can speak. It can listen and speak.
I hope it speaks better than you guys do.
It does, yeah, actually. Yeah, that's why we did it. The same with the emotion model. It's just like, we can't understand this. Yeah. So, yeah.
If a neurosurgeon was doing it, it'd be a bunch of profane in there too.
Language models are pretty simple. They just basically generate words, and it's very fluent, but oftentimes hallucinates things that aren't semantically relevant. Can you talk about the different language centers and the different types of aphasia?
Yeah, we basically have two. We label two. It's a complex network, but we have an anterior network called Broca's area, and that's the expressive area. So if I ask you to count to 5, your Broca's area will then say 1, 2, 3, 4, 5. We have an area more posterior called Wernicke's area, and that's your receptive area. For me to ask you to count to 5, you receive that. There's a fasciculus called the arcuate fasciculus that connects the two, and then you say 1, 2, 3, 4, 5. Your fluent area is Broca's area, your receptive area is back here. In your Wernicke's area, the receptive area, and start talking to that person, you could be speaking Russian or Swahili, he can't understand it. In your frontal area, the fluent area, sounds like they're talking with a bunch of rocks in their mouth, they're not fluent. So it's a very organized system of connections between reception and expression of what we call aphasias, the inability to speak. Receptive aphasia and expressive aphasia.
Is there such thing as a stroke of good luck?
A what?
Is it a stroke of good luck?
Yeah.
A phenomenon.
Where you get like
stroke of good luck would mean like when you and your brother start paying me back.
Yeah. You've seen phenomenon with where John Travolta gets like brain cancer and makes him really smart?
Pretty much.
Well, there was interesting things. If you look back in the early days, Dr. Sperry did the split brain, the right and left hemisphere.
Yeah.
And he cut the corpus callosum, connects the two.
Yeah.
And he actually demonstrated the right and left hand would fight over things because there's other things beside the corpus callosum, commissures that connect them. But when you disrupt those, there's no communication, and right and left side will actually argue.
Huh.
That's wild that's actually how it works. That sounds like a cartoon.
And pediatric neurosurgeons, in order to try to control seizures in babies before the age of 3, will actually disarticulate the hemisphere from the other hemisphere so that it can't transmit seizures to the good hemisphere. That baby brain is still very plastic, and before the age of 3, the one hemisphere will assume a lot of the duties of both hemispheres and disarticulates the seizure side so it can't interrupt the good side, and that child will develop much better.
Whoa.
Those are called hemispherectomies and things like that.
They've done experiments in cats where they actually took the auditory nerve and attached it to the vision system. They learned to hear through seeing, or maybe it was the other way around, if they're very young cats. Do we know how, when you have developing organisms, how they take in that stimulus and how it trains them to consume the stimulus when they're young?
I'm not sure I quite understand that question.
Young cats, and they've disconnected, I think, their auditory nerve and put it into the occipital lobe. It's something like that, where they
Well, the brain, I'm sure, in any mammal, if you look at the phylogeny of the brain from the rat up to the human, okay, between you and your brother, there's not much difference there, but
So rats have very smooth brains.
right,
like
it's
me
a
and Nick.
lissencephalic brain. It's very smooth.
Yeah.
And the reason is those sulci and gyri
Yeah.
allow you to increase the surface area of the brain to allow more function to elicit in a smaller space. A rat doesn't have all those gyri. So as we move up to mammalian phylogeny, we see more gyri and complex parts of the brain. Before the age of 3 in humans, and I'm sure if it's a cat or a dog, whatever, the brain has very good plasticity. It's still regenerating pathways up to about the age of 3. And that's why we don't like to use like chemotherapy and stuff in children before that, because the brain's still developing and they can't modify. After that, the brain is solid and what you get is what you get. I think in what you're saying here is before the age of 3 in a cat, or whatever that might be in the age in a cat, they're able to plastic change the function of the brain and regrow new pathways,
Got it.
which you won't be able to do electronically.
Yeah.
Is there anything in machine learning that they're trying to do with neural networks that they're looking at the human brain for inspiration or to recreate?
Man, bioinspiration, I think in engineering in general can always be a little fraught. Like, like obviously very early in aviation, they like built like ornithopters trying to like make flapping planes, kind of like in Dune.
Yeah.
And Dune
That's
2.
a very hot area right now. Interfacing electronics with the brain. We have the electronic ear, and people who've never been able to hear can now hear again. And I know they're working on a similar thing with vision. And we can make a nerve regrow. We know there are nerve growth factors, but we can't get it to go back to the target that it originally was meant for. There are neurophysiologists that are working on putting wires into all those muscles back to a computer that can make people walk again by the computer generating the pathway for walking, for instance. So interfacing neuroelectronics with the human brain is a very hot area.
Would you fly an ornithopter?
Would I fly in it? No.
No?
I don't think so.
What about backpropagation? I know that's also a hot topic right now. If the machine learning process is the same as what happens in humans.
Yeah, I think that neuroscientists have been looking for things that look like backpropagation in neurons, and you saw tons of papers where people think maybe they found it. There's something called dendritic spikes. Are you familiar with those?
I know what a dendritic spike would be in a dendrite, yeah.
There's a lot of complexity to neurons that, artificial neurons just like so much simpler. Like one artificial neuron has so little complexity that probably you would need a massive neural network to probably fully model.
What makes it a neuron electronically? I mean, I just told you what makes up the human neuron. What makes the electronic neuron a neuron?
The electronic neuron, it started with something in the 60s called a perceptron. And it's a simplified model of a neuron where there's inputs and then there's a nonlinearity and there's an output. So what that means is if you have, let's say, 1,000 inputs into your artificial neuron, each input gets multiplied by something called a weight. If it's a positive weight, it's like having a glutamate or an excitatory neurotransmitter. If it's a negative weight, it's kind of like having a GABA or what's it called?
Can be epinephrine,
inhibitive neuron
transmitter.
And then you add a bias to it. The bias, there's a similar thing with, I think, artificial neurons. You basically multiply by a number, add a number, multiply by a number, add a number, multiply by a number, add a number for every input. And then you add all of those together. So, the weights make it inhibitory or excitatory. The bias is kind of set to 0 point. And then they all get summed together. But just like the activation potential, there's a nonlinear response from the input to the output.
So if it's excitatory or inhibitory, is it based on what number is produced?
Yeah, so like let's say you have the number 3 comes in and the number 4 comes in, right? You want the first one to be activating, so maybe you multiply it by 2, so now you have 6, and then you add a bias of 1, so you have 7, right? Now you have the number 4 come in, but let's say you multiply it by -2, so you have -8, and then you add a bias of 5, so now you have -3. So you have -3 plus 7, so now you have 4. And then that goes into a function that kind of looks like an S, where there's a part where it's having very little response, and then more response, and then little response where it saturates, just like neurons saturate. Maybe number 4 comes in, and maybe that's a very small number, so it just gets suppressed to 0, basically. But let's say you now have 100 comes into the nonlinearity. It's called the activation function, and it's inspired by the action potential. So maybe 100 actually has a big response. So now maybe it's 1,000, but that's where it saturates. So you have this big, or normally it's between 0 and 1. So maybe you have zero in and then 1 come out. But now that means that neuron's firing. And that neuron is going to go into other neurons downstream. It can go into many other neurons downstream.
I understand it as a neural network, what you're trying to achieve. What makes it artificial intelligence?
We have a video about that.
I mean, it's a computer program that you're running. No different than any other computer program, just more complex.
I think artificial.
Why do you call it intelligence?
I mean, it's probably not the best label. It's a very evocative label because I think people think humanity and intelligence are pretty equivalent, and that's not true. It was a term coined over 50 years ago. I think the best working definition we have is a computer program making decisions based on information as an agent.
Isn't that always what a computer program is? You input information and you come out with a product.
True.
People think this AI is the new messiah of the world. And to me, it just sounds like better computer programs.
I agree. That's what Nico and I always say. AI just means what computers recently got good at.
Yeah, it's a better computer.
Do you think
The computer I deal with has been the same old computer for 10 million years, you know?
Let's take your thermostat, right? Thermostat takes in the temperature, and if the temperature is beyond the set point, it turns on the AC or turns on the heater. That's an agent making decisions. It's not very complicated. There's no neural network or whatever. But yeah, I think AI used to be like search or playing checkers, then playing chess. And now that's just, people just like, oh, that's a chess program.
I'm sure if this reaches out across the country to AI experts, it's going to generate a lot of, hey, what the hell are you guys saying?
Guaranteed, no AI experts watch those channels. Mostly just bots. But no, I totally agree. I think AI is for the most part, buzz term for what computers recently got good at, which is computers used to be unable to recognize objects and images. Now they're great at it. They used to be unable to engage in a long conversation with you. Now they're pretty good at it. But there's still a lot of things that people do that computers don't do. But notably, a multi-sensory organism that can navigate the world, has proprioception, different forms of inputs, has emotions, has the ability to collect energy from the environment. There's a lot of complex things people do that I wouldn't say you could test on an IQ test, but they're still very complex. And I don't think we're anywhere near getting computers to do all those things, not necessarily because it's too hard, because there's a lot of stuff, a lot of which we don't know how the brain does it. And so, yeah, I think AI, if it has one useful value as a term, is it is a die marker for where the frontier is in computer science.
You'll figure a machine out that can visually see things, maybe interface with the brain, hear things like cochlear implants, interface with the brain. But how do we deal with greed and happiness, sexual desire? How do we enter in the human factor that God himself created for us into your machine? I think that's going to be virtually impossible.
Well, I don't have a computer that can poop.
Even if you look at our speculative vision, like on Star Trek or, where they had, what do you call it when you're half human, half machine? Cyborg, something like that. Even they couldn't fully understand emotion, So I think that's where we're going to really see a deficit for maybe forever.
Well, where does that happen in the brain?
It was very complex. The frontal lobe is primarily the generator of the id and the ego and the superego. People who had frontal lobotomies lost a lot of those functions. They couldn't generate anger, they couldn't generate concern, they couldn't generate self-preservation. We've been more selective in psychosurgery, particularly with deep brain stimulation and lesioning, in helping some of these people with those problems. But it's generated primarily in the frontal lobe. Now, what allows that part of the brain to produce that function? I gave you $1 bill and you got happy. Why does that part of the brain generate that emotion? We don't know. I mean, think of the complexity in that. That can be even further transmitted to, okay, now with that $1 bill, I'm gonna try to buy something that I shouldn't buy, like drugs, or I'm gonna take the $1 bill and give it to charity. Where does that dichotomy start in the brain? And what allows you to rationalize that? Don't know.
Is the structure in the frontal lobe just fundamentally different than the rest of the brain?
It does have some different characteristics of its architecture, but not that much different. And the initiation, the spark to that. What is the spark to that thought? Your machine, you can give that spark to. We don't know where the spark comes from.
That's crazy to hear you say.
Yeah.
Somebody who literally just works with the brain all the time.
Think about that. How many times a day you rationalize something. Where's that spark to begin that thought and to finish that thought come from?
We have like our internal monologue and a sense of self. Like, do we know at all where that is in the brain?
No, I mean, people get tumors that pressure on that part of the brain or injure that part of the brain, and they will lose some of that function, spontaneity, the akinetic mutism, things like that. Where does that spark start? Where is that one neuron that began your day saying, I think I'll take my wife out to dinner tonight, or I think I'll go to the ball game tonight, or you know what, I'm not feeling good, I'm going to just call in and say I don't want to go to work. Where did that spark come from? Don't know.
Whoa.
What about planning? So like if I like think ahead, I'm like, well, I need to go do this errand, but if I go at 5, there's going to be rush hour, so I'm going to leave a little bit early.
Think about that.
So like how does planning work, and where in the brain does that happen?
Well, think about how complex that is. So you've got a task. Task is to get home. And you're saying, well, it's at 5 o'clock. My memory banks are telling me at 5 o'clock the traffic is bad. But my memory banks say if I take pathway B home, it may be a little longer, but I won't have any traffic to go by. So there must be, again, a multitude of circuits involving memory, thought, organization, perception, and then expression of what you're going to do, just to make that one little decision.
Yeah, I mean, I know a lot of the frontier in AI right now is combining search and neural networks. So like, for instance, like 4 or 5 years ago, the world's best Go and chess programs now use a combination of tree search, where you're looking through many different options like A, B, and then what happens in those options, but also neural networks that then perceive is this a good or bad situation. That sort of combined perception and planning seems to be increasingly for intellectual tasks, like a pretty critical combination for emulating human planning. Is that something where if you get lesions, like you lose that ability to kind of look ahead or explore branches?
Well, you have computer programs that do that, ways. You say, I want to go from A to B, and it examines the traffic pattern and gives you a pattern around that, okay? Where we come into play above that is, I'm stuck in traffic, I'll take pathway B. Oh, now that's got traffic, I'm going to stop and have a cup of coffee. While the machine says, well, I'll go to C, D, E, F. It may take you through New York to get there. We have the ability to subset those thought processes and rationalize them, what's best for us. Is your machine thinking what is best for itself? I don't think so.
Let's talk about hearing. How's the cochlea work?
Give me a screwdriver, I'll show you. Hearing is not that complex because we have an artificial cochlea now, cochlear implants.
Yeah.
A couple structures that have to be utilized in the ear. There's the neural part, which is the cochlea. And then there's there's 3 actually. The semicircular canals that give balance. And then there's the physical little bones and stuff that the eardrum hooked to transmit a signal to the nerves that transmit it to the brain. So there's a lot of pieces to that. If it's a structural injury like the little bones, those could be fixed and you might get your hearing back. If you wipe out the little nerves that are in the cochlea, neuro deficit like that is not rectifiable. If it's not as bad as some people think, cochlear implants may help. It may not be the way you hear, but they can relearn hearing by using cochlear implants. And then there's the semicircular canal that gives balance. And if that's injured, a good example, if you took a crawdad and injured semicircular canal, it'll swim in circles. It doesn't have the balance to understand its correction factors. But once that information enters the brain, it goes through some nuclei, the modulated again, and then it goes past the thalamus, and then it goes into the part of the brain that allows you to interpret that sound, a horn, a scream, a yell. And then what do you do with that when you hear it? If the yell, somebody's screaming, I need help, it's got to go to the part of your brain to have you respond. If it's a horn, you're going to turn towards and make sure you're not going to be hit by a car. So it too has an integration factor of extreme complexity with what you do, what you hear.
I used to work on robotic systems, and we had a robotic arm. And just
You mean the Mars rover,
Mars rover.
that never took off because you couldn't get meters and feet straight?
Yeah, that one. It's really hard to just figure out what joint angles to just like reach and pick up an object. How does the brain do that?
Well, that's that thing we talked about earlier about learning motor function, like the cerebellum swinging the bat.
Uh-huh.
So you're watching your fingers come into an object, right?
Uh-huh.
It starts up here. Now you know I got to get closer and closer. And it slows down until you can proprioceptively feel that object. If you lose the ability of proprioception, which is sensitive, you may not be able to stop when you feel it. And then you got to grab, because you see it move. So again, it's a very complex structure of proprioception, sensation, motor integration, and there are very sharp neuron fields that allow you to do that, make very quick corrections. And that's probably something a robot could learn, because if you have artificial vision and it sees its hand getting there, it'll slow down. Now, if you had sensors, just like we do, we have all kinds of different sensors in our skin, your robot, when it touches that object, will learn to stop. And you program to close, not to crush it, and bring it to you. So I think a robot can learn selective tasks like that.
So most robots, like industrial robots or even the Boston Dynamics, the dog robots, they don't use machine learning barely at all, or if at all. There's a lot of research in using machine learning for robots, but they actually just use a lot of math to figure out, like, geometrically, if you want to reach out to something, what are the angles that will get you there? And it's called inverse kinematics.
The difference between the biophysics there and the bioelectronics and the biomedicine there.
Nick once hit me in the head with a bat. Do you remember that?
Who?
Nick did. He once hit me in the head with a bat.
Yeah, I know. You've never been right yet.
I know.
You finally got smart.
Was that proprioception?
That was phenomenal.
No, it's not It's not proprioception. Proprioception is the ability to use kinesthesia, to know where I'm looking at you, but I know my hand's over here, and I know I'm touching the chair. That's proprioception.
Yeah.
Would it be fun to, if we have a notepad, to try to draw a kind of anatomy of a real neuron and an artificial neuron?
Sure.
Do you have a notepad?
Yeah.
A model of a neuron? Sure.
Yeah.
And you know what's funny? I don't know any neurosurgeon that's ever been asked to consult or help develop neural networks.
What does that mean?
Well, let's think about what we're saying here. Our understanding is so different than their understanding, but yet we're trying to interface these in a little talk like this. So you guys go home in your little office building and you say, we're going to work on this neural network for learning such and such. Could we learn from the human brain and how we develop this? You probably could. But no one ever does that. They just try to develop it de facto.
In a vacuum.
In a vacuum, brand new, just looking at the electronics part. What did God do first? What did he do that we ought to maybe take a little lesson from?
Yeah.
I'm just happy to be in a heated room, climate controlled.
You'll see how complex his drawing is. And our drawing is going to be much more simpler. So we're going to show one long fiber called the axon. And then we're going to show some shorter fibers called dendrites. And this is all taking place in the nucleus. And then the synapse at the end. And I'll draw little arrows which way the signals are going into the neuron. So there's your picture. His is over here. Look at how complex his artificial neuron is. And look at how simple, but the ability to do function on the simpler side is so much greater than the one on the left. You're getting there, but I think it's going to be a much more learned process than where we are right now.
Do you have any advice for people trying to replicate the human brain in neural networks?
Keep working. We've developed even some ability to do neurotransplantation. And that's not an easy thing to do. There are nuclei in the brain where we can take embryologic tissue, transplant it into the brain, and treat certain diseases like Parkinson's. And obviously there's a lot of ethics involved in that, and neural moratoriums on tissue and so forth. But they kept working and working and working and getting it to work. And I think what they're doing is extremely important. Even if the final pathway is 50 years from now, 100 years from now, the first flight was the Wright brothers, and now we're going to the moon. We're looking at this and going, man, it's so complex, and we're not making huge leaps and bounds. But every day is a little bit of a leap and bound. And I think the advice that I can give to all these neuroscientists is keep working and communicate. because what you're doing, I may not know you're doing, that really could accent what I'm doing. So I think the real important thing is keep working at it. In neurosurgery, we every day work on new ways to treat the human brain. Radiation, chemotherapy, lasers, immunofluorescence, all these new things that we didn't have 20 years ago, we now have. Some diseases we can cure that we couldn't 20 years ago. Some diseases are just as bad as they were 20 years ago. There's a lot that we have to learn too.
You want to say anything to our YouTube channel? To like and subscribe, or?
Well, I mean, if it's interesting, maybe your company, Gridspace, could take this to another level where we could present audiovisual models and brains and pictures to further the understanding. So if you like it, I guess, I don't know how YouTube works, you subscribe, we can carry it further, and then we can get sponsors, and then I can get free tennis shoes.
From Skechers.
From Skechers Slip-ins.
Yeah.
Incredible.